Okay, Evan, you may start it.
Hello everyone. So here's our data, the data from my group. Everyone used the same data. So we have 50 people in our sample, mainly classmates from what? What, doesn't work? Oh, okay. So we have 50 people, mainly classmates, but of course we're not 50 in the class here. So we had to ask some other friends from CYCU. So we have, I think we have an equal number of male and female, and we have so the height in centimeter and inches, plus the version with subtracted equal amount of height. So, and the weight, of course, pounds and kilograms. So, let's start. Yeah, we have here the summary statistics, well, which are not quite interesting because they are pretty much the same for everyone. But so yeah, we have here the mean body height, the mean for the height and the weight, the minimum and maximum height, minimum maximum weight, and so we have that for the two for centimeters and kilograms here, and inches and pounds here. So let's go to the interesting part. We run the regression. We get three.
Okay, just a second. Okay, so
well,
let's see the second step.
Yes.
So here we do have the overall statistics.
Yes.
Okay, but not for individual group.
What do you mean?
I mean, male and female. Separated as a male or
I'm very
female.
sorry. We forgot.
Yeah,
We
okay,
forgot
okay.
to do that.
Yeah, sure.
I'm
sure.
really sorry.
Sure.
But we can expect, as biology has its own impact on real life, right? That the mean of body height and weight is higher for male and lower for female,
Yeah, sure.
as we saw in yours. I think it was it was very well represented.
Yeah. Okay.
So we can expect the same in our data, even though the data samples is quite thin.
Yeah.
So we go to the regression model. So we have here so weights in kilograms with centimeters, the pounds with inches, and then we mixed some of the conversion value we use. We put kilograms and inches. Why we did that? Just because I feel like in the subconscious of everyone, kilograms always come with centimeters and pounds always with inches, right? And we wanted to prove that it's not just a coincidence that running these regression statistics with the same data sample but different conversion values, we get here the same t-statistics, same R squared, right? But you might say, yeah, but because kilograms and centimeters, they go along well, pounds and inches too. No, you take kilograms and inches, you're gonna get the same R squared, same statistics. Well, not the same SCD errors, never the same coefficients. Why? Because the actual values of the data being conversed, as it has been conversed, you can't expect to have the exact same coefficient. But overall, you have the same R squared and T statistic. So yeah, you can use pretty much every conversion as long as it's coherent and you use the same data sample. So let's interpret the estimated coefficient. Well, it seems like that part is not the most interesting one. We have the value we just extracted from our regression table. So here you have for the kilogram and centimeters, pound and inches. What is gonna be interesting is when we're gonna compare the equation from this regression and the equation when we were gonna add variable. Let's go. So we always have the three equation. Tell me.
Can you explain?
Yes.
Comparison
So
between these two.
here's the weight, right? It's Ry. Here we have our variable, only variable height, not height, height. So for every point increase in body height, right? You get, for instance, 1 inch, centimeters. So 1 centimeter, the weight will increase by 0.32 units. So 0.32 kilograms. And we have
So
this.
there, 0.32. You may not just use the units, since you already know the units of the weight. So now you have to say 0.32
Kilograms. Oh.
kilograms.
Yeah, okay.
Okay?
Thank you. Okay.
Okay.
Thank you very much. And so we have the same here with pound and inches. For 1 inches, the weight will increase by 1.84 pounds.
Yeah, that's right.
All right, let's continue, guys. So let's interpret the R squared. Well, it's nothing new here. We have quite low R squared, and that seems that, well, our model doesn't really fit with reality. So no. So yeah, well, here I just repeat what I already said. You use different measurement units. There is nothing that changed with the R squared because we keep the same data sample. Maybe you want to check something before.
Well, I'm just thinking about the one group just showed
Yeah. Well, yeah.
their adjusted R square, I think, is pretty high, something like 69 or 70. Then yours is just.
We get the same adjusted and R squared. Yeah. Yeah. But actually, maybe from the data sample itself, we might have not been as strict or something, because I think we have been quite strict. We didn't take higher than 1.80 m and not lower than 1.50 centimeters.
Oh, okay.
So I think the data sample is correct. And
Well, look at this. I'm just like to say that with these two different data set, and we measure the height and weight, right? And the result is quite different. Even the R square, for I think the group you have it is like 70% of adjusted R square. Then yours is something like just. Like 6%, and even with its adjusted R square, its download, no, it's lower so much.
yes. So now, yeah, we just implemented a dummy variable, which is gender, right? And well, it doesn't impacted much the R squared. It actually increased somehow a bit the R squared, but decreased the adjusted R squared just slightly. Here, actually, what would have been interesting, maybe it's like even more than that, doing the same regression analysis, but using only the male, only the female, to see in the male population how much gender is gonna like impact weight, and how for each, I'd say, like as a woman, how much is gonna. Well, okay, let's just continue. Oh yeah. No. Okay.
Okay, would you like to explain it again for the coefficient? You can just use this one. Okay, explain the coefficient of these two again.
Yes, yeah, sure. So we could do a little comparison. So if I remember well, the height have been like very slightly impacted, maybe like reduced just a bit. And yeah, we have the new variable here, gender. So depending on your gender, yeah, it might impact weight. For every okay. Okay, so the dummy variable has a positive relation that confirms our expectation. Gender does impact the weight. Actually, it also impacts the height, but it's not the point here. The only thing that is left to say is that even though it impacts, it doesn't impact much. You see, here I'm not sure which exactly we are using, but I think we're using inches. It's so slight. If your male is gonna just impact that little, so there's something that is not going well here. Why? Because our data sample is clean, has been ordered and structured well. Our regression model analysis has been run properly. So what is wrong here?
Wait. Just a second. Just
Yeah.
a second.
Go back.
Go back. Go back.
Here.
I mean, use that equation,
Yeah.
explanation, explain the meaning of the coefficient again.
Which one? Which coefficient?
This one.
So about the gender or what?
Both.
Both. So the height, if the height increased by 1 inch, I'm not really sure. Actually, I should check for you guys.
Okay.
I'm very sorry.
The measurement units.
Yeah.
Okay.
The KTV yesterday was a bit late, so.
It's inches and pounds, right?
Yeah, I think it's
Okay,
that is the case. So inches and pounds. Here we're still with inches and pounds. So 1 inches, the pound, the person's gonna be so for each increase of 1 in the height, the weight is gonna be
1 what?
Okay. Okay. For every point increase in height by inches,
Right.
the weight is gonna increase by 0.31 pounds.
That's all?
Well, then you have the gender. If you're a male,
No. That's all?
I would dare to say so. Yes.
Did I scare you? Holding gender, the variable, as a constant.
What do you mean by?
I mean,
because it's a variable.
now you have two variables, right?
Yes.
When you explain this one,
And actually, yes.
you have to say holding gender variable as a constant.
Oh, okay.
Then say
Okay. So
1 inches
holding the
increase.
gender variable constant.
Yeah,
You can say
that's
that
right.
every increase of of inches. Every increase in the height by 1 inches, the weight will then therefore increase by 0.31 pounds.
0.30. Yeah, that's
Yeah.
right.
Okay.
Okay, understand what I'm saying? Huh?
Yes.
Okay,
Yes,
then,
madam.
then explain the coefficient of gender.
So you have it's a dummy variable. So you have 0 and 1s.
Yeah.
The 0 is for female, 1 is for male. So if you're male, your weight is gonna increase by 0.93 pounds, which for me is quite low. It's like very unrealistic, right? So let's think.
That's all?
Yes, no. I hope so, really. I mean, I can explain more. I can read everything. But
No, say it again for 0.93.
Oh, okay. I think I got it. So holding the height variable
That's right.
constant.
That's right.
If you're a male, the weight is gonna increase by 0.93 pounds.
That's right.
Thank you very much.
Exactly.
Thank you very much. So, if we use this different measurement units, so centimeters and okay. Attends, je voudrais être sûr. Yeah, no, actually we were using centimeters and kilograms.
Yeah,
Here we're
okay.
using inches and pounds. So it's the same. You want me
Okay.
to repeat, or I think we everyone
That's
is okay.
It.
Okay.
That's it. Okay.
And so, what is the conclusion is that even though your theory is actually supported by scientific evidence, maybe your regression model analysis won't give a proper result, or at least the result you expect. Why? Because here the sample is very, very
different.
Yeah, small. Yeah, I assume you if you take like 1, 2, 3, 5,000 people, you will get more interesting results. But 50, statistically speaking, it's not professional to use such a reduced sample.
So do you mean that small sample? What's the difference between small sample and large sample? Since you mentioned 5 students and 50 students.
Just let me think how to put that in word. I would say that the less people you take, the more reduced the sample data you use, the higher the chances to get, I would say, exceptional values getting to matter. Because let's say you have one chance in 1,000 that one person in the world is gonna be like 10 meters tall, okay, and weighs 1,000 kilograms. Let's say, okay, and you take only a sample of 10%, but you get this person, the 10-meter tall person, is gonna how do you say that? Well, I'm sorry. Comment on peut dire ça? Yeah, well, actually, you get my point, right? The sample is gonna be there's gonna be errors.
Yeah. Okay.
Put it simple.
Okay.
I'm sorry. Didn't
That's
slip
why
much.
we say that after we collect the data, we need to
Clean the data.
To clean the data.
Yes.
We need to inspect the data. Okay. And by just looking at summary statistics, you may able to just from the minimum and maximum to see how big difference.
Yeah. And so
Those data with the other data.
Yeah, and if you take 1 million person as a data sample, if there's one 10-meter tall person, it won't matter that much mathematically speaking.
Yeah.
Even though
right.
you should still cleanse your data.
Yeah. Then again, we have different data set which also have 50 students or 50 samples, and then one with the adjusted R-square is even higher, 70%, but yours is only 2%, right?
Exactly.
Right. So looks so different.
Yes.
Okay. All right.
Okay.
Okay.
Thank you for your attention.
Thank you very much. So then, Crystal? This is your turn.
And I'm going to present my assignment, and this is the data set we had retrieved from our friends, and we rate from the higher to lower, and this is the gender, and then male and then female. And this is the height in cm and weight in kg, and this is the height in inches and weight in pounds. Yeah. And
You can have this one. Yeah, okay.
do I need to enlarge it?
Hit this one.
Oh.
In order to shift.
Oh.
Yeah, okay.
And here's just the data, and then we had the height, height and weight for the minimum, maximum, and the sample size, and we didn't separate into two groups like male and female, and we just used the we just put two genders in one, and the mean for height in cm is 17.82, and the weight in kg is 58.67, and the height in inches is 6.07, and the weight in pounds is 129.05, and the minimum height is 5, which means it is 155 cm, and the weight in kg is 35, and the height in inches is 1.02, and weight in pounds is 77, and maximum height is 33, and the weight in kg is 95. The height in inches is 12.05, and the weight in pounds is 209, and the sample size is 50. And we had run the regression, and okay, the weight in kg and cm, we had run the regression in kg cm, and then weight is pounds and height is inches, and then we compared in kg and inches. And for the comparison of kg and cm, we can see there is when there is 1 cm higher, there will be an increase in kg of 1.22, and then for the pounds and inches, we can see that when this is 1 inch higher, there will be a increase in pounds of 6.79, and for the comparison in the middle, which is kg and inches, we can see the data is times 2.54, so we can see the relationship between the two data measurements. Correct?
And all this coefficient?
Oh, okay.
This is
you
just
mean-
the output. Okay. So that's just step
Oh.
2.
You
okay.
mean this?
Yeah.
So, see. Oh. Do I have to mention it again? Because there's for the unit in kg and inches, the weight increased by 3.98 kg, while increasing in 1 inch. And for units in pounds and inches, the weight increased by 6.79 pounds, while there is 1 inch increase.
Okay.
Okay. And the equation 2.6, we can see that we have the same positive result that is similar to equation 2.6, and the only difference is because of the data, the numbers are different.
Okay.
And for step 5, can you find out adjust R square in the result? And we can see the adjust R square is 0.57, while the range of adjust R square should be between 0 and 1. And our result is in the middle range, and which is we consider this a not a failure because it's not very good or not very bad. And this means that we have 57% of variation from weight that can be explained by height, while 43% of variation from weight cannot be explained. Therefore, we think we may have to add other related variables to make the adjust R square more higher.
Okay.
And for step 6, and we had add male into our equation. And the first photo is the kg and cm, and the photo on the right is pounds and inches. And we can see that when male is because the dummy variable is 1 when it's male and it is 0 when it is female. So when the we had the two equations, like when what will happen if it is 1 and 0, and we can see that the weight of male is higher than female, because when the gender is 1, which is male, there is 3.98 increase in the weight. Therefore, when the D is equals to 1, which is male, the weight will be higher. So for female, as it is 0, so there will not be any increase in the weight in our equation. So for the comparison of pounds and inches, it's also the same, because we can see the weight of male is 99.07 and the weight is 19. But the weight for female is 90.31. So we can see that for both measurements, the weight of male is higher than female.
Okay.
Yes. So yeah. So it means that the gender has a high impact on the result. So gender has a relationship to weight.
Okay, go back. Okay, can you explain those coefficients?
Okay. When you mean like hold them?
Yeah. Okay. Any one of them, either
CM and KG.
Yeah.
Okay.
Either one of them is okay.
When there is an increase in the height in cm, it is
Increase in
cm.
1 cm.
1 point.
Measurement units
Yeah.
is cm, so it's 1 cm.
Okay. When there's increase 1 cm, it is wait a minute. It is 1 kg heavier.
Huh? 1 kg heavier?
I'm a bit confused now. When there is 1 cm higher, there will be one
Coefficient is there.
do I have to say agenda first or the C?
It really doesn't matter. When say complete sentence.
Okay.
Yes.
I forgot how to start how to say the equation. It is 1 cm higher and there will be an increase of 3.98 hold
Which coefficient do you explain right now?
the gender.
Gender, okay. So what does that mean?
It is 1 cm high. When there's increase in 1 cm, there will be. I forgot how to say it.
No. We have two coefficients.
Oh,
Do it separately.
oh. So when there is increase in 1
You know,
cm,
It looks very easy job, but it is so difficult to do the explanation. So far for every one of you, it looks easy, right? Okay, say it again for these two coefficients.
the cm and gender.
No, you have to explain it both.
The 1.01 and 3.98, you mean?
Yeah,
Oh.
yeah.
So when there's 1 cm increase, there will be 1.01 kg increase, and when the
Complete? Finished?
and hold you mean holding gender in constant?
Yeah, holding gender variable as a constant.
Yes.
Then
there will be an increase in
1 inches, 1 centimeter
cm.
increase in height.
Yeah.
Then
there will be 3 point.
no. Since I already holding gender as a constant, how can you explain the coefficient of the gender? When you say holding gender variable as a constant, right? Then you can explain the coefficient of the height.
So there will increase in 1.01.
Say it again. Say it again.
Is holding for the when there is 1 cm height 1 cm increase
In height.
in height, and there will be 1.01 kg increase,
Right.
and then
No. Finish?
holding the gender in constant.
Yes.
Okay.
Holding gender variable as a constant. Then 1
So-
inches.
Wha-
1
1
centimeter higher
Yes.
increase.
Mm.
The weight will increase by 1.01
Holding-
kilogram.
uh,
Okay, now explain the gender, the coefficient of the gender.
So there will be one when coefficient
The coefficient of gender is
3.98.
3.98. Explain this coefficient.
So when the gender is male, there will be 3.98 increase in weight, which is the kg, and then holding height in constant.
Yeah. Okay. Okay.
Yes.
So holding height, usually is easier to just, say those holding variable as a constant first.
Mm.
Okay, so holding height variable as a constant.
Yes.
Okay. When the gender is male, okay, then the weight will be increased by 3.98 kilogram. Okay?
Okay.
Make sure everybody know how to do the explanation. Okay? It's very important. Although looks easier. Okay?
Okay.
All right, thank you very much. Now is Jackie. Where is Kevin today? Huh? Okay. Then Daisy is not here today, right? She's absent today, right?
For Kevin, I heard he won like 3 or 4 millions at the lottery, so now he's just in the Caribbean. Just went to the Caribbean with his millions.
Oh, really? You're kidding. Oh, okay. Then, 那个这个，对，然后这两个把它当，对，这个。You know what? You listen to your partners do the presentation. Okay, you can ask yourself when he or she do the presentation. Okay, then what you hear from what he said, you need to ask yourself: do you say the same thing, or do you know how to express in your way? I think the very, very important things now for this course is the explanation of your output instead of those math. Okay, I not really emphasize all the math. If you just understand the math, but you cannot explain all the output, it's useless. In real world, people wanted to say or wanted to hear what's the meaning or what's the information for all these outputs instead of all the math. Okay? Although the math behind is important. Okay, that's we need to learn some math behind. But we're not really focused on the math parts. Okay? This is very application course. So I don't want all of you, don't know how to do that interpretation. This is the major parts for this course. Do the explanation of the output, computer output, okay? And especially this is for statistical, mathematics methods output, okay? It's very important to do the explanation. All right, go on.
Okay, so this is the data we collect from our friends in college, and there are 50 observations there, and 25 for male and 25 for female. Okay, and this is the height in centimeter, weight in kilogram, height in inches, weight in pounds, and the value of the height is that we use the original height divided by 2.54 and minus 60. The 60 means the inches, 5 feet. I mean 5 feet. Yeah. And so step 2, the mean in height in centimeter is 18.22. The maximum height is 36, which is 156, and the minimum height in centimeter is 5, which means 155 centimeter, and sample size is 50. And weight in kilogram is 59.08, and maximum weight is 95, minimum 35, and sample size 50. Height in inches 6.22, and maximum 13.22, and minimum 1.02, and weight 129.97, and maximum 209, and minimum is 77, and sample size is 50. And I do not find the maximum and minimum in gender. Yeah. And Wrangler regression, according to the statement on textbook, the x variable should be height, and y variable should be the weight. So we hypothesize, and we think that the taller you are, the more weight you get. So we hypothesize the estimated equation will be like this: weight height equal beta little plus beta 1 height. And after we put the data into the eViews, we got the estimated equation like this, and the units is in weight is kilogram, and in height is centimeter above 150. And this is the same in pounds and in height, in weight and height. Okay, and then we generate another equation so as to compare the relationship between the x variable. So we use the y variable in pounds and x variable in centimeter, and then we got this estimated equation. And after compare these two equation, we can find out if we multiply this value, multiply 2.54, and this is the and it equal to 6.05. Yeah. And step 4, interpret the estimated coefficient. Okay, so the left-handed is like if the height increases 1 centimeter, the weight will increase 1.08 kilogram, and if the height increases 1 inch, the weight will increase 6.05 pounds. And compared to the equation 2.6, we think we have different estimated coefficient with this because the data we collect is quite different, and maybe the units we use is also different.
No, one of the measurement units is the same.
I mean the pounds and the inches.
The inches
Yeah.
is the same as the
It's the same with the equation.
textbooks.
So is the left one is different.
Only using the kilogram and centimeters, but measure in different units. Right?
I know. Yeah, right. So is the data we collect are different. Yeah. So and step 5, interpret R bar square, and so the R bar square we get is the same 0.56. Yep. And the meaning of R bar square is like to deal with the problem that R square has.
Excuse me. The official name is adjusted R square. The
Okay.
notation may be different.
Oh, okay.
Okay, in our textbook, they are using R bar square, but some of the books is just using R, then subscripts A square. So no matter what kind of notation, but the official names for this is called adjusted R square. Okay, so it's better to use adjusted R square.
Okay, so
Okay.
adjusted R square is like to deal with the problem that R square has. The problem R square has is like the higher the R square is, the better the equation it is. So But there is a problem. Is like when we put a new variable into the equation, the value the value of R square will increase, and even we put a nonsensical, which means not relationship with the y variables, the R square value will also increase. So to deal with the problem, so we have the adjusted R square. Yeah, because it also put the numbers of variables into consideration. Yeah.
But so far here, we just have one variable.
Yeah, right.
Yeah, okay.
Right.
So here, usually we're using just R square instead of adjusted R square.
Oh.
Adjusted R square is used for multiple regression.
Okay.
Okay. Usually it's for multiple regression.
Okay.
Okay.
And step 6, a second equation. Okay, so so according to the statement, we need to put another x variables, which is gender, and we also hypothesize that the more weight you get, the taller you are, the more you get. Yeah, so we hypothesize the equation.
Hey, excuse me. We hypothesize the taller you are, the more weight you get. What do you mean by the taller you are?
I mean, like, what I want to convey is like.
Oh, you mean the height?
Yeah, the height. Yeah, yeah.
Okay, okay.
So the sign should be positive.
Okay.
Yeah, the sign should be positive, and the gender is either male or female. So it's like a dummy variable. So the estimated equation will be like this.
Okay.
Yeah. And after we put the data into the eViews, we got these two estimated equation. And I think, and if the, should I explain the coefficient?
Yeah, sure.
Yeah, okay,
Sure.
so holding gender as a constant, yeah. So and if the height increase 1 centimeter, the weight will increase little at 0.0 kilogram. Yes, and holding height as a constant, and if the gender is male, and the weight will increase like 5.1 kilogram. And so, and is there any relationship between weight and gender? So if we put if the dummy variable equal to 1, and then we got the equation like this. So, and if the dummy variable equal to 0, which is female, we got the equation like this.
How did you get this one?
Oh, I typed it wrong. It should be 0.8.
0.8,
Yeah,
right?
Yeah.
Okay.
Should I revise it?
Okay. All right.
Okay. So it's like if we, it's like if we have the same height, the weight of the male will like heavier than the female. I think it makes sense. It's because like we know like men usually have more like muscles or wider bones. Yeah, so I think it makes sense. The equation makes sense. Yeah.
Okay. All right. That's it.
Yeah, that's it.
Okay. All right. Did you see the R square, adjusted R square for the second equation? What's the difference between the adjusted R square with
with the previous one?
the first one with the simple linear without gender variables? What's the difference?
Okay, let me see. I think it increases.
Okay, one is about 56%.
And, yeah.
Now with the gender, just the R square becomes to
Almost the same.
just add a little bit,
Add a little.
increase a little bit only. Okay? All right, so there not much difference.
Not much. Yeah.
Okay, all right. All right, so that's it, right?
Okay.
Okay, thank you.
Thank you.
Then, okay, never mind. Let's have a break. Okay, then we will have the last group. Okay.